Today, we see the cutoff and saturation points for a transistor connected in common emitter mode. Okay, cutoff and saturation points. These points are very important. And how do we find these points? We drew a DC load line. In previous class, a few classes back, we had seen how to draw a DC load line. Okay, we did it for a common emitter circuit. So the DC load line that is shown here, on the x-axis we take VCE, collector emitter voltage, and on the y-axis we take IC. And using the equation, we know the equation is this: VCE equal to VCC minus IC RC. So using this, we had drawn the DC load line. So that is shown here. This is the DC load line here. And here what we have done is we have the output characteristics superimposed over the DC load line. The output characteristics for IB equal to 0 is shown here. Base current 0, and this is for some value greater than 0. And this is the saturation value, the maximum value of the IB, the maximum IB. So we have the output characteristics over this load line. And when we look at this, we see a point where the load line intersects the IB equal to 0 curve. Okay, the point where the load line intersects the IB equal to 0 curve. That point is here. This is IB equal to 0 curve. Okay, this is the load line. It is intersecting at this point. And that point is called the cutoff point. Okay, this point is the cutoff point. Okay. And here the base current is 0 because the load line is intersecting with IB equal to 0 curve. So base current is 0. So naturally the collector current will be 0, or there may be a small collector current IC or leakage current. And here what happens is the base emitter junction is no longer forward biased. So at the cutoff point, the base emitter junction is not forward biased. We know for a transistor to work properly, base emitter junction should be forward biased, and collector emitter junction, that has to be reverse biased. So here the base emitter junction no longer remains forward biased. The saturation point. Okay, after the cutoff point, another point is the saturation point. It is a point where the load line intersects the IB equal to IB saturation curve. This is the IB equal to IB saturation curve. Okay, and here is the load line, and load line is intersecting here. So at this point, we have the saturation, the maximum base current. Okay, and the situation here is the base current is maximum, and the collector base junction no longer remains reverse biased. Okay, the collector base junction has to be reverse biased. Okay, for a transistor to work properly, the base emitter junction should be forward biased, and collector base junction has to be reverse biased. Base current maximum means the saturation means it is no longer reverse biased. Okay, so at this point the base emitter junction is not forward biased. Here the collector base junction is not reverse biased. In between these 2 points, the saturation point and cutoff point, the junctions are properly biased. That is, the base emitter junction is forward biased and the collector base junction is reverse biased. Okay, so the transistor actually has to operate in the region between cutoff and saturation point. Okay, we know in the active region, as we said earlier, collector base junction is reverse biased, while the base emitter junction remains forward biased. Okay, so in the active region is the region between cutoff and saturation. There, the transistor is properly biased. Okay, so the transistor will function normally in this region. So this is the active region. So what we saw is the cutoff point, the saturation point, and then the active region. And we always take enough precaution that the transistor is always in the active region between the cutoff and the saturation point. The transistor biasing, an important concept of the transistor circuits, the transistor biasing for faithful amplification of a signal. Basically, a transistor is used for amplification of the signal. Okay, for faithful amplification, we will see what is meant by the faithful amplification. The amplifier must satisfy 3 basic conditions: proper zero signal collector current. Okay, zero signal, that means even without the presence of the signal, proper zero signal collector current should flow, proper base emitter voltage, proper collector emitter voltage. Okay, so these 3 basic conditions has to be satisfied. So the process of raising or amplifying a weak signal without any change in its general shape, that is called faithful amplification. Okay, faithful amplification is the process of raising the strength or amplifying a weak signal without any change in the shape. Okay, that is the faithful amplification. So for faithful amplification, the transistor amplifier has to satisfy these 3 conditions: the proper zero signal collector current, proper base emitter voltage, proper collector emitter voltage. Okay, the first 2 conditions ensure that the base emitter junction shall remain properly forward biased during all parts of the signal. Okay, so the first 2 conditions ensure that base emitter junction remain properly forward biased. The condition 3 ensures that the base emitter junction shall remain properly reverse biased at all times. Okay. The condition 3. So essentially all these conditions are meant to keep the base emitter junction forward biased, collector base junction reverse biased at all times. Okay, so this is actually called the biasing of a transistor. It ensures that as I said earlier, the base emitter junction is properly forward biased and collector base junction is properly reverse biased during all parts of the signal. So we will have faithful amplification. There will not be any change in the shape of the signal. Okay. For this can be achieved either using a bias battery. Okay. By using 2 batteries, one in the input circuit, the other in the output circuit, so that it always maintains the forward bias of the emitter base junction and reverse bias of the collector base junction. Second method is by using a circuit, associating a circuit with a transistor. So instead of using batteries, that is costly, instead of that, we use a circuit for biasing the transistor. Okay, so the second method, this is more efficient and is frequently employed. Okay, so the circuit which provides this is not known as the biasing circuits. And there are different biasing circuits available. Let's see the first one, the base resistor method. Okay, base resistor method. So as the name indicates, it will have a base resistor. So that is shown here. You have a transistor, a base resistor connected here. RC is there, a collector resistor, and plus VCC. There is only one power supply. And here VCE is the voltage between collector and emitter, and VB, that's the voltage between base and emitter. Okay, so let's see how the base resistor is able to maintain a constant current IB flowing through the base, and hence the collector current IC through RC. When we look at this, look at the input part. This is said to be the input part. Here plus VCC is the voltage applied here. So plus VCC that is equal to VB plus IB RB. Okay, that is very quite evident. As the base current IB flows through RB, we will have IB RB, the voltage drop here, and here the voltage drop the between base and emitter, the voltage drop is VBE. So if you add VBE plus IB RB, you should be getting VCC, because the potential difference between this point and this point is VCC. So that is given here, IB RB plus VBE equal to VCC, and from this we can find IB. IB is VCC minus VBE by RB. VB is 0.7 volt for silicon, and it is 0.3 volt for germanium. This VBE, this is 0.7 volt for silicon and 0.3 volt for the germanium, the base emitter voltage. Okay, and beta, we know that is IC by IB. So from this we can find IC. IC is beta IB. And now applying this Kirchhoff's voltage law to the output circuit, this portion. Here the drop is ICRC, and the voltage drop between collector and emitter is VCE. So VCE plus ICRC, that is equal to VCC. Okay, so that is shown here for the output circuit. And VCE, that is VCC minus ICRC. For IC I can write beta IB, because beta is IC by IB. Okay, so we can get these equations. So these resistors, essentially the base resistor here, that maintains a constant voltage, a constant current through the base, and proper biasing is introduced. And these are the various equations. Using this, try to attempt this problem. We have a transistor circuit biased using base resistor method. We know what is RB, RC. RB is 470 kilo ohm, RC is 2 kilo ohm, VC is 12 volt. Beta is 100. We want to find IB, IC, and VC. Given VB is 0.7 volt, that is we are IB, IC, and VC. Okay, we have the equations with us. So using that, try to find IB, IC, IB, first find IB using this equation, and then find IC, and once IC is with us, we can very easily find what? VCE. VCE this VCC minus ICRC. So attempt this problem. And these are the answers that you should get to IB 24 microampere, IC 2.4 milliampere, VCE 7.2 volt. Okay.